All right, we're going to spend some time working with radicals in this section. First, some properties of radicals. Again, this might be a bit of review, but just to make sure that we're all clear on these. First, this is just the definition, this first property, the definition of the nth root. The nth root of a to the n is equal to a, and likewise, the nth root of a raised to the nth power is equal to a. We can either split up or combine a radical over multiplication. As long as we can combine the radical over multiplication, as long as it's the same index of the radical. If we take a root of a root, so if I have the nth root of a and then I take the mth root of that, this is the nmth root of a, right? So you multiply those indices. This is just an application of the fact that we can multiply exponents when we raise a power to a power. So the mth root of the nth root of a, this is a to the 1 over n, all to the 1 over m power. And we know that we're allowed to multiply these exponents. So that's 1 over nm. And that is the definition of the nmth root of a. We can combine radicals over division if they are the same index. Again, it's the nth root and the nth root, and that gives you the nth root of a over b. And you can also split up that radical. Right, so properties 2 and 4 work in both directions. Just a note of caution, we cannot split up radicals under addition or subtraction. We've learned this in previous semesters, but this is a really just important thing to keep in mind whenever I am working with either exponential or radical expressions and I see addition or subtraction. I just make myself slow down and not do something silly like split up a radical over addition. We're going to simplify some radicals. Now, I'm going to show you a couple of different ways to simplify this one. Basically, if you're simplifying a square root, you're looking to take out perfect squares. Similarly, if you're simplifying a cube root, you want to take out perfect cubes. So if we start by just factoring 75, 75 is 25 times 3, I could rewrite this as the square root of 25 times 3. And I'm choosing to rewrite it this way because 25 is a perfect square, so I can split up a radical over multiplication. This is the square root of 25 times the square root of 3. And I know that the square root of 25 is 5, so I get 5 square roots of 3. So this kind of depended on me like recognizing the perfect square when I saw it. Another way to do this, and we'll get the same result, is when you're factoring, factor all the way. So 25 is 5 times 5. And so this is the square root of 5 times 5 times 3. Now this is a square root, right? So there's actually, we don't write it out for the square root, but really the index of this radical is 2, right? And whatever that index is, it tells you how many of the same factor you need inside in order to take out one factor and bring it outside of the radical. So we could take out a 5. Now when we take that 5 out of the radical, now they're both gone from inside the radical. And whoops. And we're just left with 5 times the square root of 3. And that's the same thing we got. For numerical radicals, you can always check to see that you did it right. There's no variables here, so I can, on my calculator, take the square root of 75, and it gives me this numerical result. And if I take 5 times the square root of 3, it should give me this exact same result. And it does, digit for digit. Let's try another one. We're going to take the 6th root of 8. Now 8 just factors as 2 times 2 times 2. So it looks like we're looking for 6 of the same factor in order to take one out. And obviously, we don't have 6 of the same factor. We have 3 factors of 2. But sometimes we can change the index or the order of the radical. So maybe I don't have to write it as a 6th root. And the way we do this is to go use the exponential form. So this is the 6th root of 2 cubed is 2 to the 3 over 6. Now 3/6 I can reduce, that's 1/2. And 2 to the 1/2 is the square root of 2. So here we have reduced the order of the radical. And again, this is a numerical result, or numerical radical example that we're working with, so we can actually check on the calculator. We can find the 6th root of 8. Now you can find the 6th root of 8 in your calculator. If it has it in the menu, you can hit the math key, and option 5, where there's a little X there in the index, choose option 5, and then it will be looking for you to plug in the index or the order and the radicand, and there's that, and then I can compare that to the square root of 2. If it doesn't look like your calculator allows you to input a radical of different orders, if I want the 6th root of 8, I could just take 8 and raise it to the 1/6 power. Now right now, the way that my calculator is set up, it knows that the whole thing is in the exponent, and there we go, that works. Now if you have an older version of the operating system on your TI-84, or if you're working with a TI-83, I can show you how that'll look. When you take 8 and you want to raise it to the 1/6 power, now you just see the up caret. So you got to put this in parentheses, 1 divided by 6 parentheses. If you don't use parentheses, it'll take 8 to the 1st and then divide the whole thing by 6, and that won't give you the result that you're looking for. Okay, so we kind of saw this process happen a little bit, but here we have like basically the simple procedure. If you want to reduce a radical to simplest form, remove all perfect nth powers from a radical of order n, and then if possible reduce the order of the radical, like we saw that we could do in this example. We were able to reduce the order of the radical. So let's simplify this. This is a square root, so we're not going to reduce the order of the radical here at all unless, you know, it happens to be a perfect square and we don't need a radical. But I don't think that's going to happen here. We want to take out perfect squares. So look, I'm going to rewrite the stuff inside. And I'm going to choose to rewrite this as a squared times a, and then times b squared. Because this is a square root, I need perfect squares. So here I have a couple of factors of a. So an a squared comes out as just an a single factor of a to the 1st. A b squared comes out as a single factor of b to the 1st. So we have a, b sitting outside this radical, and the only thing that's left, because those guys go away, the only thing that's left is a factor of a inside. Let's try another one. We're going to simplify this radical. It's a 9th root, so we're going to start by, 9th root here. Let's see, I've got a 3 cubed, I've got x to the 6th, and I guess if I'm looking for 9th powers, I could see here that I could take out a, or I could write that y to the 12th as y to the 9th times y cubed. And now I could take out this y to the 9th. So there's the y. That goes away. But everything else seems to stay. Because I don't have any more perfect 9th powers. But maybe we can reduce the order of this radical. And the way that we try to do that is to use the exponential form. So instead of the 9th root, I'm going to raise it to the 1/9 power. And we can distribute this 1/9 power to all 3 factors. And When we distribute this, we'll have a power raised to a power. So we're going to multiply those exponents. So we're going to have 3 to the 3 over 9 times x to the 6 over 9 times y to the 3 over 9. And reducing the order or index of a radical really boils down to, can we reduce the fraction exponents? So 3/9, 6/9, 3/9, those all reduce. So this is 3 to the 1/3, x to the 2/3, y to the 1/3. And if we want to write this in a simplified radical form, now we're going to do one more thing and get back in radical form. This stuff right here, there's a common denominator, right, to these fractions, which means I can write that stuff in the red box as a radical of index 3. So this radical, or this denominator of 3 in those powers, corresponds to me taking the cube root of 3 to the 1st, x squared, y to the 1st. And there is the simplest radical form. Just looking back at this example, when you're checking to see if you can reduce the order of a radical, usually what you want to look out for is do all of the exponents inside the radical, do they share any common divisors with the order of the radical, with the index of the radical? Alright, now we're going to rationalize some denominators. There are some circumstances where it's useful to leave a radical in the denominator of a fraction. It's not very conventional to write fractions that have radicals in the bottom, and usually if something's in simplest radical form, that means we eliminate radicals from the denominator. We call this process rationalizing the denominator, and the technique is really quite simple. So first, in this first example, I've got the square root of 2/5. So we don't like radicals in the denominator. We don't like fractions inside a radical, right? So if we see radicals, we really just want it to appear like in the top of a fraction, or maybe just not in a fraction at all. So the first thing I'm going to do is actually split this up, split up this radical over division. So we got the square root of 2 divided by the square root of 5. So now I can isolate. Here's the issue, is that I have the square root of 5 in the bottom, and the technique for getting rid of this is quite simple. We're going to multiply the top and the bottom of this fraction by the radical square root of 5. We're allowed to do this, right? We're allowed to multiply the top and the bottom of the fraction by the same thing, right? Anything we want. The square root of 5 is helpful, though, because in the bottom we have the square root of 5 times the square root of 5, and we know that if you multiply square root by itself, that just gives you what's inside. So now there's no more radical down there. Up top, the square root of 2 times the square root of 5 is the square root of 2 times 5, or square root of 10. And that's as far as we go. Now there's no more radicals in the bottom. Be careful, we cannot reduce that fraction. 5 goes into 10, yes, but we don't have a factor of 10 up top. We have the square root of 10. You can only reduce and cancel common factors when they're either both inside the radical or both outside the radical. So the 5 is outside the radical, the 10 is inside the radical, which means we can't do any reducing here. Alright, let's take a look at another example. We have 5 divided by the square root of 18. We're going to begin. Now you could look at this, and if your instinct was, I'm going to multiply the top and the bottom by the square root of 18, that would be fine, and you'll get to the same correct result. It might just take a couple extra steps at the end. When I start this process, I always simplify any radicals I see first. So 18 is 9 times 2, and 9 is 3 times 3. So I'm going to begin by simplifying this radical by taking out a 3. So I have 5 divided by 3 times the square root of 2. Now when I look at this fraction, I say, okay, the problem really in this fraction is I got the square root of 2. So I'm going to multiply the top and the bottom of this fraction by the square root of 2. And on the bottom, the square root of 2 times the square root of 2, that's a factor of 2. I'm going to multiply it by the 3 that's already there. So in the bottom I've got a 6. Up top I have 5 times the square root of 2, and that's as far as we can go. The 2 will not cancel with the 6 because the 2 is in a radical and the 6 is not. And I'm going to do one extra bonus example here, and that is suppose I was you know, all the ones we've done so far focus on square roots. If I had an example, let's say I have 1 over the cube root of 9. So I don't want radicals in the denominator. Now, if I rewrite this, this is 3 times 3. Here's the catch. If I took that first fraction, 1 over the cube root of 9, and I just multiply top and bottom by the cube root of 9, that actually won't get rid of the radical. So with cube roots, remember, I want 3 of the same factor inside in order to take one out. And I've already got 2 3s. So to rationalize this denominator, I would simply multiply the top and the bottom by the cube root of 3. Because that will get me the cube root of 3 times 3 times 3. And that's just a 3 on the bottom, and on top we have the cube root of 3. So you're basically just adding in factors to get you to a desired number of the same factor inside the radical, is how this works. One more quick one. If I had 1 over the cube root of 12, 12 is 2 times 2 times 3. So what I would multiply by on the top and the bottom, first of all, it's going to be a cube root for sure. I want a single factor of 2 to bring me to 3 2's, and I need 2 factors of 3 to bring me to 3 3's. You just build up so that you have the same, you know, the desired number of factors inside. So up top, 2 times 3 times 3 is 18. So I got the cube root of 18 divided by 3 times 3, let's see, this would be, I got 3 2's and 3 3's, so that's 2 times 3, or 6. So a couple of bonus examples there for if your radical is a different order. Okay, let's do one more. We're going to simplify this. So, okay, I'm slowing myself down a little bit. I see addition, so I'm not going to do anything hasty. I know that I cannot split up a radical over addition, and also I see a negative exponent. So that -2 exponent is only on the b. It's not on the 2 there. So I'm going to begin by rewriting this. It's a square root, and I've got 1 over 2a squared plus 2 over b squared. Now I can't split up the radical over addition, and because I don't have a single fraction inside, there's no division for me to split it up over. But I could get a single fraction inside if I just add these fractions. So let's get a common denominator. I'm going to multiply top and bottom of the first fraction by b squared. I'm going to multiply the top and the bottom of the second fraction by 2a squared. So the denominator of this fraction is 2a squared b squared. Up top I have b squared plus 4a squared. Alright, we're making progress. Now that I have a single fraction inside, I can split up this radical over division. And I'll notice in the bottom I have a couple of perfect squares. I can simplify that radical. Right? These guys are going to come out. So on the bottom I have AB times the square root of 2. And up top I have b squared plus 4a squared inside a square root. And now what I need to do is rationalize, right? I've got that square root of 2 in the bottom. We don't want to leave that there, so we're going to multiply both the top and the bottom by the square root of 2. So in the bottom, now what I have is 2ab. Up top, I'm multiplying two square roots, so I can combine them under a single radical, which I'm going to do. I've got 2 and then times b squared plus 4a squared. You could choose to distribute the 2 through the parentheses or not. I'm going to leave that as it is. And there we are.